In today's lab experiment, we are going to be doing a little bit of calorimetry. So we are going to be building a very simple calorimeter that can be used ultimately to collect data that you can calculate enthalpy, delta H, change for any particular process. And we're going to be looking at a really simple chemical reaction. We're going to be looking at baking soda and vinegar. Okay, so this is our actual chemical equation that you've seen before of sodium hydrogen carbonate, solid, plus acetic acid, goes to carbon dioxide, water, and a salt sodium acetate. And we're calculating our enthalpy value. So enthalpy ultimately is associated with the heat transfer associated with any particular reaction. So we need to look at heat transfer. And what a calorimeter does is it isolates the heat, essentially, of a reactant and its surroundings inside the calorimeter. So you can measure how temperature changes for essentially the surroundings as best you can once that chemical reaction takes place, and the bonds break, the bonds form, you either absorb heat energy or you release heat energy to the environment. The idea with the calorimeter is that we're actually isolating a small portion of the environment and measuring the temperature change associated with it. If the chemical bonds absorb heat, you're going to see the energy associated with the temperature associated with the surroundings contained in here go down. If it releases heat, you'll see the temperature inside that styrofoam cup associated with the surroundings go up. Now, you might be saying, well, how can we isolate the surroundings when essentially all we're adding are the reactants, right? Baking soda and vinegar. Well, it turns out that our vinegar, it's really only the acetic acid that's reacting, and it's a really small component of this solution. This is primarily water, and water is going to be our surroundings. So we're containing and measuring the temperature of the water, which is the bulk of what you're going to have in here once we mix our two reactants. And from that temperature change, figuring out the heat that is absorbed by the surroundings or released by the surroundings, and relating it back to what must have happened for the two reactants, the baking soda and the vinegar, the acetic acid, that are dissolved in that water. Okay, so this is our very imperfect calorimeter that's been built here. It's just two styrofoam cups, right? Styrofoam does a pretty good job of insulating, so protecting what's inside from the outside in terms of heat exchange. And then we've got another beaker here that's just serving as a stand for the styrofoam cups so that they don't accidentally knock over. We also are going to need to measure temperature change. So with that, we actually have, this is a temperature probe that is associated with a data logger system that we have here. It's called the Verniers LabQuest, and so here's the little handheld data logger. And these work really nicely. They just have a connection that we can plug into one of the channels that are up on top of the data logger. And it should self-identify that this is actually temperature that we're plugging in here. Yep, it does. And so we can see that now it's reading. The room temperature here is 18.1 degrees Celsius. Okay. Now, what we want to do, we want to get a baseline temperature before our reaction happens for the bulk of that surroundings, the water inside here. But of course, our water is coming in the form of the water that's found in the vinegar. So we're going to measure out our first reactant, 50 mils of vinegar, and add it in here, and then start taking the temperature while we prep our second reactant. So to measure out my 50 milliliters of vinegar, I've got a graduated cylinder here, 50 milliliter. Please use a graduated cylinder, not a beaker, to actually measure out your volumes. Beakers are, these markings on the side really are just suggestions. They're guidelines. They're not calibrated, essentially, whereas graduated cylinders are considered volumetric measuring devices. They are calibrated. This one actually has its rating on the side. It says plus or minus 0.4 milliliters. So we can feel fairly confident about the volume readings that we get off of here. Now you'll see I also added a small funnel. This is just so I don't spill vinegar all over the place. This is a huge jug of vinegar here. So I'm going to make my life a little bit easier and pour just a little bit into a smaller beaker. And that just makes it easier for me to actually dispense it. Now make sure you get down on eye level as you read this. And if you need to, as you get closer, you can always grab a barrel pipette to add the last little bit. Okay, so I'm almost there. I'm just going to grab a barrel pipette and get the last little bit. So this is a barrel or transfer pipette, right? It's just a little squeeze bulb here. And we're just going to take that last little bit. Oops, I'm going to have to add a little bit more of my vinegar here. Okay, there we go. The bottom of my meniscus is right on that 50 line, so I've got exactly 50 milliliters plus or minus 0.4. And we can dispense this into our calorimeter. Now I'm just going to lower my thermometer, my temperature probe here that is attached to a ring stand, to a clamp to a ring stand, and that just lets it sit there. Okay, and we're going to let the vernier equilibrate to the temperature of the water that makes up the bulk of the vinegar for a few seconds while we actually get our baking soda ready to go. So in this reaction, the vinegar is actually in excess. We have more acetic acid dissolved in that water than the amount of baking soda. We're going to make sure that baking soda is actually our limiting reactant. So the moles of baking soda that we add are ultimately going to control this entire reaction and how far it actually proceeds. So the idea then, to make sure that this is the limiting reactant, is to add about 2 grams of baking soda to this container. So we're going to measure that out on our balance here, and I've got a piece of weighing paper that I've just creased a little bit to actually, that's a little dirty. I've got a piece of weighing paper here that I have creased a little bit just to make it easier to transfer over the baking soda after I'm done. We're going to tare that by pressing the tare button. Okay, and it returns 0. And now we're just going to add some of our baking soda. It doesn't have to be exactly 2 grams. We are going to record, though, exactly what we do measure out, because that's a vital part of our data. So we're going to go with the 2.17 grams. So here's the starting point for my reaction. my data so far: 50 mils of vinegar combined with 2.17 grams of sodium bicarbonate. Now, the great thing about the vernier data logger is that it's going to record all the temperature measurements for us, and we don't have to sit here and stare at a thermometer hoping to catch the peaks in temperature, the minimum and the maximum temperature, where we might start and end. So all we have to do, though, in order to make sure that it captures that data, is we actually have to start data collection. So the thermometers come with a preset time-based program that lasts about 180 seconds. You'll see that actually if you're looking directly at a LabQuest. It's in the upper right-hand corner. These little gray boxes show you the length of time, 180 seconds, and 2 samples. So once we press the little arrow button on the LabQuest itself, what it's going to do is start collecting data for us over 180 seconds. It's going to do 2 temperature readings every second and just graph that actually for us. So that's all we have to do before we add the baking soda. We need to capture that initial temperature before we add the baking soda. So we're going to press that start, and it starts collecting data for us. It brought up a graph, and now it's getting those initial temperature readings for the vinegar, our initial temperature. And we let it go for a couple seconds there. It should collect a few data points. And then we are going to take our our baking soda and just dump it in here. Ooh, and we get lots of fuzzing. Okay. So I have a stir bar that I'm just stirring here, capture to make sure that everything is well mixed as this happens. And you can keep an eye on your LabQuest and the temperature change once it starts to rise again. So it turns out that this dropped in temperature. It went down. Right now it's reading about 13.9 degrees Celsius. And we'll just keep stirring away here. That's 13.8. So we can just stir for that full 180 seconds. It's only 3 minutes. That's not long. When it starts to rise again, though, make sure it really is rising. When it starts to rise again, you can stop data collection. Okay, so now we've got our graph. The glare on that screen may make it hard to actually see, but it is actually a line that starts up here at about 17.2 degrees. It drops once I added the baking soda, and then it kind of levels out. It does actually decrease for quite a long time, so I do recommend trying to go for the full 180 seconds and collecting temperature that full time. Now, in order to get our data, we are going to basically use what's called the statistics function. So at the top of the screen, and again, I know this is kind of hard to see on the actual camera, but hopefully I'm getting the glare off of there. At the top of the screen, we've got several different headings or menu bars. We're actually going to go to the Analyze menu bar. These are touch screens. They're not the most sensitive. They do come with a little stylus, most of these, if it hasn't gotten lost over time, that you can use to try to do this a little bit more precisely. But we press on Analyze, it brings up this drop-down menu, and we are going to go to Statistics. And we're going to ask it to give us the basic statistics on temperature. And those are actually going to get reported over here in this gray box on the right-hand side, but you can actually just press on it and it'll bring it up bigger. And the basic statistics that it returns to you are your minimum, your maximum, your mean, your standard deviation, and the number of data points that it collected. So for this particular experiment, because we're looking at that change in temperature, we want to know what the min and the max is. And you have to have noticed on that graph that we started at 17.2. So don't just assume that we're always increasing temperature. Our initial temperature was actually our max. Our final temperature was our min. So this gives us our data points that we need in order to calculate the enthalpy for this particular reaction.